Let us now discuss about linear regression model. Even before we proceed, I want to explain you all about a very simple equation which is well known to most of the people. And that is a simple equation which says y is equal to f of x. What does this mean? Any output that you want to achieve either depends on a single input or it might depend on multiple inputs. All right. So either the output that you want to achieve depends on one input or multiple inputs. And there's the equation y is equal to f of x. This y is called as output variable, x is called as input variable. We would be looking into an example where output is influenced by a single input. And this is what we would try to accomplish using Tableau as well. And by the way, this is an inbuilt feature within Tableau to construct a linear regression model. Having known about this equation, let me also tell you that the output variable of interest data type is pivotal in determining on which regression technique we are going to employ. For example, if this output variable of interest is continuous, if you all forgot on what continuous variable is, then if you can represent anything in decimal format, that variable is called as continuous. If you cannot represent something in decimal format, it is called as discrete data. So if the output variable of interest is continuous, irrespective of what your input variable is, we employ a technique called as linear regression. And if we have only one input which influences the output, then we call it as simple linear regression. If there is one output which is continuous in nature and which is influenced by multiple inputs, under such circumstance you call it as multiple linear regression. However, we'll be focusing our discussion only on simple linear regression. All right. Now, another thing that we need to bear in mind is this equation. This is called as equation of line. If you all remember from your school days, what is the equation of line? Equation of line is y is equal to mx plus c. Remember, I'm taking you guys back to your school days, where m is called as slope of the line and c is called as y-intercept. Y-intercept. All right. On similar lines, we have this equation. It's the same. Instead of y-intercept c, you're giving a different notation called beta naught. And instead of the slope called m, we are giving another notation called as beta 1. These beta naught, beta 1s are called as parameters of the prediction model that you're trying to build. And epsilon is called as error. We'll discuss each thing in detail. And we'll also try and understand on what is least square estimate. Before that, this output variable of interest y is also called as dependent variable. Another name given to this is output variable or dependent variable. The variable x is called as input variable or independent variable. Now all you need to do is, if you're trying to plot y and x, you do a scatter diagram with all the data points like that. And when we do this prediction model, it would automatically come up with this line. which is a straight line, which is also called as fitted line or predicted line. The straight line is called as fitted line. And this is the equation y is equal to beta naught plus beta 1 x. How is this line determined? Why can't I draw a line like that? Why can't there be a line like that? Why can't there be a line like that? In this way, there are infinitely many number of lines possible. How is the best line determined? It is determined based on something called as least square error or ordinary least square technique. When you draw a line like that, you drop a line from each and every data point to the line equation, and you try to find out the distance between each and every point to this line. How do we calculate? So any point that is represented on a two-dimensional scale would have, say for this data point, it would have an x and a y representation. So on the x-axis, it lies here. On y-axis, it lies there. So you'll have x and y for each and every data point. And on this line also, this specific point would have x and y. Say that this specific point here is x2 comma y2. Now if I were to find out the distance between these 2 points, x1 y1 and x2 y2, I can use something called as Euclidean distance, and there are many other ways of calculating the distance: Euclidean, Manhattan, Mahalanobis, so on and so forth. We'll stick to this. It is square root of y2 minus y1 whole square plus x2 minus x1 whole square. You get the distance of this data point from this line. In that way, you calculate the distance of each and every data point to the line, and then add the entire thing, and then look at what is the overall distance coming up to. So what is that value coming up to, right? For this specific line. Also, what you do is, on similar fashion, you draw another line, another line, another line, infinitely many lines, and you calculate the distance of each point from that new line, and then add it up and see which of those lines is giving you the least distance, and that would be your fitted line or the straight line. And hence it is called as ordinary least square value, because we are always focused on the least distance. All right. Another thing is epsilon in the equation, right? So how is that calculated? Or epsilon is the error term, and it is given using this equation, which is predicted value minus actual value. What does this mean? Say you're predicting that sales for a specific company for the next quarter would be $1 million. You have predicted this. But would it exactly be $1 million? May or may not be. What if the actual happens to be $0.9 million? Right? Hence, the difference between the predicted value and the actual value will give you the error, which is represented using epsilon. Yep. Now, that is the error basically, right? So these data points are your actual values using which you have come up with the scatter plot. These data points are all actual values. All the data points for that case are actual values. And this line is going to give you the predicted value. And the distance between that actual value and the predicted value is called as error term. We will do this practically also using a case study, so you need not press the panic button yet. Now, how is the strength of the prediction model determined? Strength of the prediction model is determined using a value called R squared value. This R squared is also called as coefficient of determination. More the R squared value, better is the model. Higher the better. And this R squared value always ranges from 0 to 100%. And if the R squared value is greater than 0.8, you call it as a strong correlation. Your prediction model is very good for predicting the future. And if this R squared value is anywhere between 0.65 to 0.8, it is called as moderate correlation. Yeah, statistically, this R squared value would be explained in this way. I'm going to tell you the statistical definition. If you like, you can consume that, or you can go with the thumb rule that if R squared value is greater than 0.8, you have a very good model for prediction. Now, this R squared value represents percentage variation in output, which is explained by the input variables, or percentage of response variable variation that is explained by its relationship with one or more predictor variables. The response variable is another name given to your output variable y. Predictor variables are x's, inputs. These are all the different names: dependent, independent, input, output, so on and so forth. Okay. Now, we know also for a fact that probability associated with a single value is always zero. Probability associated with a single value is always zero. Hence, we are going to calculate the confidence interval for a given value. Say you want to predict the sales of your company for the next quarter. You should never give a single value. We know why we shouldn't give, right? Instead, we give an interval. Within intervals also, we have two intervals, and Tableau uses confidence interval, not the prediction interval. So I'm going to discuss about confidence interval. We have already discussed rather in the previous sessions on that. Confidence intervals represent a range within which the mean response is likely to fall. So if you have the output, if you take multiple samples, you get multiple outputs. If you take the average of those, it should fall within this range. And that is the definition of confidence interval. Now let us look into a small case study, post which we are going to discuss about the case study, and we will solve it using R, try to understand the finer nuances, and then we will go back to Tableau and try to accomplish a similar kind of activity there. Now here, if you want to learn more about prediction, interval, so on and so forth, I would request you all to look into our course on statistical analysis. We have, through XLR, also provided statistical analysis program, which is even more exhaustive than what we are discussing here. All right. So here is a case study, the waist circumference adipose tissue case study. Here is a business problem. Studies have shown that individuals with excess adipose tissue in the abdominal region have a higher risk of cardiovascular diseases. Chance of you getting heart stroke, etc. is higher. And CT scan, commonly it is called a CT scan, which is computed tomography, is the only technique that allows for the precise and reliable measurement of adipose tissue at any body site. However, there are a few problems associated with the CT scan, and those include these. Many physicians do not have access to this technology. Irradiation of the patient is going to suppress the immune system. and it is considered to be expensive. So, what is a simpler yet reasonably accurate way to predict the adipose tissue, which should be easily available, which should be risk free and inexpensive? And here is where a group of researchers have thought, let us check whether we can predict the adipose tissue area using very simple anthropometric measurements, that is, measurement on the human body. And that is where they have come up with this study wherein they thought, let us see whether waist circumference is a good measure to predict the adipose tissue area or not. And they have started collecting the data of patients, and they've collected 109 data points, meaning they have collected the data from 109 patients. And we have the waist circumference and adipose tissue. And the waist circumference is, you know how it's measured. I need not tell you that. Adipose tissue in this historical data is measured using CT scan. All right. So adipose tissue is measured using CT scan. Waist circumference is measured using the normal tape, measurement tape that we have. Given this data, it's extremely clear that you want to predict the adipose tissue, which is the output variable of interest. And we have waist circumference, which is input variable of interest. And now using this historical data, we need to build a prediction model. Let us first try to solve this using R. Again, the reason why I'm using the tool R is because R can be integrated very easily with Tableau. Tableau has an inbuilt functionality to connect to R seamlessly. Hence, we would be building this prediction model in R to get accustomed to R. So what are we waiting for? Let us try to solve this case study using R.